Good afternoon, and welcome to Hand-Wavy Chemistry, where we do not delight in the details, but rather bask in the big picture. Today, it's problem time, where we answer chemistry questions. In my last hand-wavy guide video, I talked about how FID NMR works. Today, we'll be following up on this by analyzing some NMR spectra in order to determine the identity of an unknown chemical species. So let's get started. The NMR spectra we're going to be examining today come from the website WebSpectra, which is supported by Cambridge Isotope Laboratories and the UCLA Department of Chemistry and Biochemistry. They group the questions into beginner, intermediate, and advanced, but do be aware that some of them do involve analyzing infrared spectra as well. Before jumping into these questions, make sure that you have an NMR reference table, something that summarizes whereabouts different peaks should appear based on their chemical properties. If you are a student, your teacher most likely has already given you one. If you don't have one, a quick Google search for NMR reference table provides a lot of different options. Make sure that you find one that you are comfortable with and that you understand. I like this one from the University of Calgary because it shows the chemical structure associated with peaks in different positions, making it very clear to visualize what types of fragments could be involved. Here is the first problem. We've been given the molecular formula as C4H8O2. I've shown all of the peaks up above and then zoomed in down below. The red lines are referred to as integrals. They represent the relative amounts of protons in each state. We can see that the first integral is about 2/3 the height of the next two. We know that there is a total of 8 protons, so 2 plus 3 plus 3 is 8. So I'm comfortable saying that this peak here at 4.0 has an integral of 2, so there are 2 protons in that state. This one at 2 has an integral of 3, and this one at about 1.2 also has an integral of 3. So now we need to start to think about what types of environments these protons are in. The peak at 4 is indicative of an NH or an OH or a proton that is bound to a carbon that is attached to electron withdrawing groups. We know that there is no nitrogen, so we can ignore NH. It's also not going to be an OH because of the coupling we see. We can see that that peak expands into 4 others. So this is going to be a carbon with 2 hydrogens attached because we said it has an integral of 2. And also an oxygen, which is the electron withdrawing group that is shifting this peak position out to about 4. The peak just below 2 is a singlet with an integral of 3. We expect this to be a CH3 group attached to a carbon that has no protons on it. Remember, the number of peaks is equal to the number of adjacent protons plus 1. So if we have a single peak, there are no adjacent protons for it to couple to. So if we go back to that peak at 4, we said it had 2 protons attached to a carbon attached to an oxygen. There are 4 peaks there. 4 minus 1, 3. It must be attached to a CH3 group as well. But it must be a different CH3 group to the one at about 1.95. So we're expecting that last peak there at 1.2 to be a CH3 group. And indeed, it has an integral of 3. It splits into 3 peaks, so it should be attached to a CH2. So what we're doing here is we're building up fragments. And we're going to have to start to put those fragments together. We are still missing 1 carbon and 1 oxygen, with there still being 1 carbon and 1 oxygen unaccounted for. If you were to ask me at this point what I think the structure is, I would think that it is an ester, with the following structure: CH3, CH2, then our ester moiety, and our CH3. This would account for the coupling we've seen so far. Now we'll look at the carbon-13 spectrum and see how that aligns with this prediction. Here we have the carbon-13 spectrum. I haven't bothered to zoom in on these peaks because there's no additional information to be gained. This thick branch here we can ignore, as that is the solvent peak for CdCl3. This peak out here is indicative of a carbon double bonded to an oxygen. It's also shorter than all the other peaks, which is a sign that it is a quaternary carbon, which means that there are no protons attached directly to it. The next peak would make sense for a carbon with a single bond to an oxygen, and these two peaks here both align with what we'd expect for alkyl carbons. That is, carbons that are just attached to hydrogens and other carbon atoms. This spectrum agrees with our prediction. We can even start to assign some of the peaks. The carbonyl peak, well, that's going to be this one. The carbon attached to an oxygen, well, that's this one. And then we have our two CH3s that are on the end, and those are going to be the two circled peaks. Our second question is for a chemical with the molecular formula C9H10O3. When I look at this spectrum, I immediately think it has an aromatic ring system. That is due to the peaks at around 7 and 8 ppm. When we zoom in on them, we can see that they are both doublets. That is to say, they are each 2 peaks. So each is next to a non-equivalent neighbor. This pattern is indicative of a para-substituted benzene ring, like so. If this is indeed the case, each of those peaks represents 2 protons. So our integral here is 2, and this one 2. Looking at the last set of peaks, we can see that the integral ends up being about 3 times higher. So this is a total of 6 protons. When we zoom in, it looks like it could be a doublet, but that doesn't make sense. Instead, what I think we are looking at is 2 CH3 groups that just happen to be close together, and there are no protons on the adjacent atoms. If we look at these fragments we've drawn out, we will see that we have 8 carbons, 10 hydrogens, and no oxygens. Now those 2 CH3 groups, they're close to 4. In problem 1, we noted that when a peak is close to 4, that is easily explained by attaching an oxygen to the carbon, like so. So we're still missing 1 oxygen and 1 carbon. So there's probably a carbonyl, a C double bond O again. So at this point, if you ask me to put these fragments together, keeping in mind that there's probably a carbonyl group as well, I would be thinking the structure is probably something like this. So let's now take a look at the carbon spectrum and see if it also agrees with this type of structure. And here we have the carbon-13 spectrum. Remember, this is a solvent peak, so we're going to ignore it. Now if we do a quick count for the number of peaks, we see that there is 1, 2, 3, 4, 5, 6, 7, which isn't 9. However, the peaks I've labeled 3 and 5 are twice the height of any other peak, so could actually represent multiple carbon atoms. Peaks 1, 2, and 4 are very short, so those would be quaternary carbons, carbons with no protons on them. And peaks 6 and 7 should be our CH3s. So now when we start to work through this question, we can assign some of these peaks. As I said, 6 and 7, these are going to be CH3s. And we have 1 at each end of the molecule we've got drawn above. So that's fine. Peaks 3 and 5, they are going to be these carbons here. And you can see that there are 2. They're in exactly the same environment. There is a mirror plane running through this molecule. So we would expect 3 and 5 to be about twice the height of 6 and 7, which they are. Peak 4, I'm going to assign to that carbon there because it is aromatic, it is attached to another carbon, and it has no hydrogens on it, which explains its short appearance. So peaks 1 and 2 are going to have to be this carbon and this carbon. And it's not obvious from just looking at this which is which. So yes, the carbon-13 spectrum agrees with our structure. Now, some of the problems involve additional information besides just a proton and carbon-13 NMR spectrum. For example, this question, problem 30, involves a DEPT or DEPT spectra, a COSY spectrum, and an IR spectrum, each of which contain additional information. A DEPT spectra helps you to identify the number of protons attached to a carbon. A COSY spectrum lets you know which protons are next to each other. And the infrared spectrum, well, that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a question you'd like to see answered in a future problem time, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.